Now that you know a little bit about how parallel streams work, I want to talk in a bit more detail about how to avoid common programming hazards when you use parallel streams. And these are not quite the same. They're a little bit the same. There's some overlap with the discussion of common programming mistakes, which we made a couple weeks ago when we were talking about sequential streams. Those are just things to watch out for in general when you're using a stream, like don't forget to put a terminal operation at the end, or don't forget you can only run a stream one time. Those were examples of common programming mistakes. This discussion is going to focus more in terms of hazards of concurrency and parallelism when you use a parallel stream. So it's more specified or more customized to the issues of parallel streams processing. And the main thing to be careful of is the streams framework assumes there's no race conditions when the different elements run in parallel. And remember, of course, what's a race condition? A race condition is a problem that arises when your application depends on the sequence or the timing of the threads running on the different cores in order for it to operate properly. So you have race conditions if your program depends on the order or the timing, and then the order or the timing doesn't go as planned, in which case you'll end up with race conditions, which are bad, because you'll have strange results. So the easiest way to avoid this stuff is simply make sure that you have behaviors with no side effects. If you don't have side effects, then you don't have race conditions, because there's no shared mutable state. So that's the easy way. Now, that's not always possible, but if you can do it that way, that's great. And a lot of the way the streams are designed with splitterators that take the data source and break them up into chunks, those are deliberately designed to try to keep things as independent as possible. But sometimes there's behaviors that depend on some shared state. I'll give you some examples as we talk a little further about this. So first thing to remember, avoid stateful lambda expressions. What does that mean, right? So this example here is a little contrived. I'll give you better examples in a second. But this example is what not to do. I guess it would be easy if you weren't really familiar with the concept of what streams was trying to do. So this is the Buggy Factorial example. We've looked at this before. And what's going to happen here is we're going to have state that's accessed in this example that will be changing when the different threads are running in parallel. And it will be shared mutable state. So the Buggy Factorial example is one we've looked at briefly before. It might make more sense now that you know a bit more about streams. So this is a factorial that's trying to compute n factorial. And it's taking parameter n, and it's going to return the n factorial of it. And the mistake it makes is that it has shared mutable state. Namely, there'll be one instance of this class called total. And that class called total has a shared mutable field called mtotal. So there'll be one instance of total, and therefore one instance of mtotal. And then when we go ahead and compute the multiplication of the range of values from 1 to n, inclusive of n, we will end up sharing that state. So that mtotal field will be accessed and, more importantly, updated, because it's mutable, right? It's shared mutable state that's the problem. It'll be mutated anytime mult is called. It'll multiply mtotal times n, and then update itself, because that's as you can see, it's basically an updating operation. So it's times equal n. That'll update mtotal with the current value of mtotal times n. And then it updates itself. So that will be problematic, because if these things are running in different threads, you'll end up with different threads simultaneously updating the same shared mutable state, which will lead to chaos and insanity. So that's a bad thing. You don't want to write code like that. Now, it turns out to be remarkably easy not to do this by simply using other features like reduce, which doesn't have these problems, and getting rid of the use of a single variable here. But the point here is don't do this. Another problem, which we touched on before in the context of sequential streams, but which simply becomes even more problematic with parallel streams, is interfering with the data source itself. So you want to make sure, as is discussed at this reference here, that you don't change the source that you're streaming over while you're in the process of streaming it. So don't change the source of the stream within the pipeline itself. So here's an example. This is a variant of what we looked at before. Just used a little bit different collector here. So we're going to make ourselves a range of integers from 0 to 9, or 0 to 10, but we don't include 10. We box them into, we have a range of ints from 0 to 10, non-inclusive. We box them into integers, and then we collect them, and we're going to collect them into a collection, which is an array list. So we're going to have an array list collection. So we have a list of these things. And then what we're going to do is we're going to go ahead and iterate through that list in parallel, and we're going to go ahead and remove each element as we're peeking at it. And this will just have the craziest results. And if you go back and run this example, it'll demonstrate for you just how pathological this will be. It'll throw weird exceptions and blow up and definitely not get the results that you're expecting here. And that's because we're modifying the underlying collection as we're streaming through it. So make sure you don't do that, especially in parallel. It'll be even more messed up because, as you might imagine, the list that's returned by toCollection array list new is not thread safe. So it's not expecting to have things change. Not supposed to be changed in the first place, but it definitely doesn't want to have things changed as it's iterating through it, because you'll have race conditions on top of other problems. So if you have no shared state in your behaviors, if you have no side effects in your behaviors, life is very, very simple, because then there's no need to do any synchronization. So the easiest thing to do is just rely on the streams features that partition the input up into chunks, and then make sure those chunks all operate with stateless behaviors, and problem pretty much solved, assuming you implement things in a sensible way, which is pretty easy. And here are some examples. So if you take a look at the various behaviors that we pass into these intermediate operations in our search stream gang program, you can see that these behaviors, like search for phrase or is empty, they're entirely self-contained. They don't have any side effects. So obviously, getting the size of the list doesn't have a side effect, just reads the size. The one that goes ahead and makes this new search results object using a splitterator, which we'll talk more about later, that also is self-contained. There's no shared state. There's no shared mutable state. We're not updating a collection or something. We're doing everything within the context of that one thread. So it's trivially stateless, trivially thread safe. However, you can't always do it quite that way. It's not always the case that you can make everything partitionable such that there are no dependencies. And here's a very simple example from the application. This is the image search gang example, or image search stream example that we'll look at later. And this is actually a bit more like your programming assignment. If you were to look deep in the bowels of your programming assignment, you'd see that internal to your programming assignment and internal to this example, there's a map that's used to keep track of the images that you've downloaded, so you can go and look and see if you've already downloaded an image before. It's basically a cache. And obviously that cache is meant to be shared by all the threads, because if you didn't share the cache by all the threads, then each thread would have the opportunity to have duplicate images, and then you'd end up doing extra processing. So in that particular case, we're going to have a shared mutable object, namely the cache map, and we want to make sure that that cache map is thread safe. So the easy way to do something like that is simply to use the concurrent hash map, and that is trivially thread safe because it's got all kinds of advanced locking mechanisms with so-called segment locks and really clever optimizations that are lurking underneath the hood there. And if you're curious in how concurrent hash map works, if you take the class I'll be teaching this spring on the second half of this, which is kind of concurrent object-oriented programming, we'll talk a lot more about concurrent hash map, and you'll see how it works. So best approach is not to have shared state, then problem trivially solved. The best way not to have shared state is to have lambda expressions or method references that don't have any side effects. If you can't do that because you have to share something, like in this case we share a cache, in that case make sure you use data structures that are thread safe. And ideally, the best thing to be able to do is use data structures that are not only thread safe, but intentionally designed to be very efficient in the face of concurrent access, like concurrent hash map. So those are just some tips to keep in mind. For this course, you don't have to think too much about that because we have designed things to be embarrassingly parallel, and cache management is all handled under the hood by the things in the image crawler framework. But when you write your own code later for other things, you may have to be aware of this. Yes, Gavin? So take while and drop while are designed to work correctly when run in a sequential stream or a parallel stream. But I think, as I'd mentioned very briefly when we talked about take while and drop while, they're not really very efficient for parallel processing. And that's because they have to do all this coordination internally in order to make sure that they get the longest sub-prefix or the longest grouping of things that match if the input is ordered. And so it's a little bit more tricky that way. So yeah, there's certain things, and in fact, we'll talk more about this when we talk about the pros and cons of streams. Certain aggregate operations, especially intermediate operations, work with parallel streams. They just don't work very well with parallel streams. And we'll talk about that. And that's kind of by design. It just turns out that you can make things work, but there's a lot of extra work required in the implementation of the streams framework to make them work correctly. So it adds extra overhead. So some things will work with parallel streams, but you won't necessarily get a win. And we'll talk a lot more about that when we talk in detail about how parallel streams work under the hood. In fact, that's the whole point of that discussion, is to know how parallel streams work under the hood so you can make a better choice about which features to apply, knowing their implementation characteristics and the overhead therein. But yeah, that's a great question. Okay, so that's just kind of an overview of how to avoid these concurrency and parallel programming hazards when using streams.